So another important problem I wrote is the parallel plates problem. It turns out that large flat metal plates, and by large really all I mean are like 5 centimeters long, which is large on the atomic scale. If you have large flat metal plates and you charge them up using a power supply, you may recall from your Science 9 days that from a battery that was positive, that was negative. You charge them up with a power supply, either a plug or a battery. Usually one plate labeled plus for higher voltage is charged to a large positive voltage, 500 volts, 300 volts. And another plate labeled minus for lower voltage is left grounded, so it actually has a voltage of 0. If the metal plates are very large, and again, by very large, I mean really just like this, 5, 6 centimeters, because on the atomic scale, it is very large. The voltage varies directly with the distance from the plates. Say what? I'll show you what that means. Let's suppose, don't write this down, just watch. Suppose this was 1,000 volts, and this was 0 volts. What that means is to travel from here to here, you go through 1,000 volts. But even more than that, Grayson, let's suppose that this distance here was 5 centimeters. What's the voltage from bottom to top? What's the distance? It means each centimeter you travel, you go through 200 volts. If you're halfway there, you've gone through exactly 2.5 centimeters, 500 volts. That's what I mean when I say the voltage varies directly as the distance. It's a nice, lovely linear relationship. Go halfway there, you've gone through half the voltage. Go 1/3 of the way there, you've gone through 1/3 of the voltage. Go 1/4 of the way there, you've gone through 1/4 of the voltage. If you want a specific example, let's imagine that we have plates separated by 5 millimeters. So these are very, very close together, and charged to 500 volts. Make a graph that says a voltage. I'm not going to do that, but for what it's worth, every millimeter you would travel through 100 volts. You would. If we were to graph this, we would find something kind of cool. I'm going to skip that in the interest of time, and I'm going to say, here's what you would find. You would find that the voltage drop ratio is constant over distance. And here is the key. It turns out this ratio is the electric field. The electric field between parallel plates is constant. The electric field between parallel plates is constant. If I were to draw the electric field between these sets of plates right here, first thing I would have to figure out is the direction. How do I figure out the direction of electric field? Well, I ask myself a question. What question do I ask myself? Which way? Some of you are in trouble. That's forces like repel, unlike attract. Which way would a positive want to move if it could? So don't write this down. Let's suppose there's a positive right there. If the top is positively charged and the bottom is negatively charged, which way will it want to move? Down. Which direction is electric field? Which way will it want to move? Which direction is electric field? Yes. There should not have been a pause there. Which way will it want to move? A positive wants to move down, the electric field is down. If I wanted to draw the electric field, this I do want you to write down, I would go like this. And then to show that it's the same everywhere, I would draw more lines parallel and exactly the same distance apart. Here is a picture of a uniform electric field between parallel plates. I tried to draw them all parallel and the same distance apart. Write that down, please. Because I will be asking you a question similar to this sometime in the future. If I wanted to show that they were not uniform, this would be incorrect, because somehow I'd be saying right there the electric field was weaker. Because remember we said how far apart the electric field lines are is how strong the field is. That's why I tried to draw them the same distance apart. Or if I had another electric field line right there, that would be wrong, because I'd be saying, oh, it got stronger right there. That is not the case. Now, you might be, if you're curious, saying, why, Mr. Dueck? There's two explanations. There's a mathematical one, which I'll do in a bit, but there's an intuitive one. I'm going to go back to this diagram. Don't write this down, just watch. Here's a positive charge. Which way does it want to move? Why? Two reasons. The top positives are doing what? Like, repel. Now, unlike attract, but these unlike charges are not that close. The force of repulsion is much stronger. But as it moves down, it's going to be getting closer to the negatives, so they're going to attract it stronger. But at the same time, Rob, as it moves down, that repulsive force is going to be getting smaller because it's getting further away. You have a lovely constant force because as you move further down, your repulsive gets weaker, but at the same time, in exactly the same amount, the attraction gets stronger. You have a constant force. And the only way you can get a constant force, if F equals EQ, is if you must have a constant electric field because the charge isn't changing. So that's the intuitive explanation. There's a mathematical one we'll do in a second. It also allows us to calculate the electric field. It turns out the electric field between parallel plates is equal to the change in voltage divided by the distance. Now, we've measured electric field in newtons per coulomb. But now you know another way to measure electric field. What's the top of that fraction's units? Volts per meter. Remember when I talked about gravitational field, I said gravitational field had 2 units, newtons per kilogram or meters per second squared. And when I brought an electric field of newtons per coulomb, I said there's another way to measure it too. This is the other way to measure it. It's volts per meter. This is also, though, going to be a problem. Look up, don't write this down. Last day, we calculated electric field from a point charge like that. And the way we figured out that that was the equation to use, you may recall, someone said, oh, that's the right equation because there's a distance in the picture. There's meters in the picture. Problem. That's meters. That's meters. So that trick that we used last lesson isn't going to work. However, I picked my letters very, very carefully. What does the letter R stand for specifically? You use that when there's round circular point charges. I used a D because it's the distance between the plates. It's not circular. So now we got several ways to find electric field. It's a scalar equation. You put a vector on there? Yeah, I add the vector by saying or asking which way would a positive want to move if it could. And it's always from a higher voltage to a lower voltage, from positive to negative. Example 2 says, find the electric field and the direction inside the plates. Don't write this down. This would be wrong. Why? Yes, there's a distance, but it's not between 2 or 1 point charge, not from a point charge. How can I find the electric field? You can write this down. Between plates, it's going to be the voltage divided by the distance between the plates. Shaq, if you look at the picture, if I go from here to here, how many volts do I go through? Look at the picture. Say it with authority. You're right. Shaq, what if instead it said 100 volts here? How many volts? What would my change in voltage be? 125? Shaq, I'm just trying to give you every possible weird permutation. What if it said negative 100 volts there? What would my change in voltage be? Careful. Oh, sorry, what? No. From positive 225 to negative 100, how far is that? How many volts have you gone through there? Positive 325. right? 225 to negative 100 is a voltage of 325. Those are the three that they'll throw at you, but Nate, almost always actually they'll just have the right hand, the grounded voltage, the negative voltage as 0, because instead of attaching it to a battery, you'll attach it to the ground. So, Shaq, in our example, what did you say the change in voltage was? You were right. Not in my modified. That was the modified. What did you say the first time? 225. So, with authority. What's the change in voltage? What's the distance that we travel through? Thank you, Mickey. You did the conversion, 0.03. Which is what? 7,500? 7,500 what? It's electric field. Now, if you said newtons per coulomb, I'd give you full marks, although I would say volts per meter, because that's what I used as my equation. Direction. Which way would a positive right there want to move if it could? From positive to less positive. To the right. By the way, Mickey, what did you say the distance was? What did you say the distance was? How many volts would I have traveled through if I went exactly halfway? 112.5, half of 225. This is why parallel plates are so nice. The voltage is nice and linear. Oh, and the electric field is constant. The electric field anywhere in here is 7,500 volts per meter, no matter where you are. Actually, I fibbed. Can you all go back up to this drawing? Turns out, on the very, very ends, the electric field is a bit distorted, and this is why, no matter how good your TV was, it was always a little bit blurry. Okay. For what it's worth. Nerd moment, but I have to point that out. Example 3. Turn the page. How does the electric field, it asks, at point X compare with the electric field at point Y? I've already told you the answer. I've told you the answer is they are the same. What we're going to do is prove it. So there's the punchline. Here's the joke. I'm going to write an equation for the electric field. Come on, pen. Oh, it's been doing so good. She's been doing lousy. Pause the screen. I'm going to go Vx equals, and I'm going to go Vy equals, and Vx is going to be, sorry, V, Mr. Dueck, I want the electric field. I apologize. I was thrown off by my pen going haywire. And we've said that electric field is voltage divided by distance. Electric field is the voltage divided by the distance. I guess that means the electric field at location X is going to be the voltage at location X divided by the distance to get to X. And the electric field at location Y is going to be the voltage at Y divided by the distance at Y. Okay. Going from here to here, what's the distance at X? Don't say 2. 0.02. What's the total voltage going all the way across? 500. What's the total distance all the way across? So how many volts is each centimeter? So 2 centimeters, which is location X. What's the voltage there? 200. I think the electric field at location X ends up being 10,000 volts per meter. I did the math in my head, but I'm pretty sure I'm right. Is that okay, Mac? Let's repeat for location Y. At location Y, now that is the whole voltage, 500, divided by the whole distance. And Rachel, I think you also get 10,000 volts per meter. I said to you I'd give you an intuitive explanation as to why the electric fields are constant and the same. Here's the mathematical explanation as to why the electric field's constant and uniform anywhere in this parallel plates. The electric field in this example is 10,000 volts per meter. It says prove it. There, you just did. No, point Y would be all the way across. I'm going to start at the same, because this is technically, good question, Mickey. Technically, this is a change in voltage and a change in, I should have my initial be the same for both of them. Otherwise, I'd be doing nonsense. By the way, Mickey, what you're saying, though, in terms of voltage is, yeah, that's 200 volts to get to there. From here to here would be 300 volts, but that's not the electric field would be how many, well, you could say I went through 3 centimeters and 300 volts, and I'd also get 10,000 volts if I go 300 divided by 3. I get the same thing no matter what. Now that's different in example 4. These electric fields, comparing A and B, I mean here, here it's constant. Here, for a point charge, it's changing. Yuckier math. Much yuckier math because of that R squared. It says explain your answer using principles of physics. We just kind of did. So I haven't yet convinced you why parallel plates are so nice. They are. Next lesson, I will use this to explain how lightning works. Okay? We'll talk about how that all works. Because it turns out you can think of a cloud as a huge parallel plate. Don't care about the top, but the bottoms of thunderheads are flat. That's a parallel plate. Not metal, but the physics is going to work. Little technical comment here. Here's the third explanation. It's a graphical one as to why the electric field is constant. It turns out if you were to graph voltage versus distance between parallel plates and from point charges, the voltage versus distance from parallel plates is a straight line. The voltage versus distance from point charge is a curve. And the slope of each of these is electric field. How do you know? Because volts per meter rise over run. Here you have a constant slope, a constant electric field. Those that are in calculus know here you have a changing slope, changing electric field. So I wrote here, since electric field is the slope of these graphs, we see that it is constant between plates, large close to a point charge, really huge close to a point charge, and gets smaller as you go further away, and it doesn't get smaller in a nice straight line. It's yucky. I said to you I was going to try and give you a better analogy for voltage. For everything that I've done so far, I've tried to relate electricity to gravity. In fact, I've said that charge is very similar to mass. You've even heard me say or talk about big Q as being the big planetary charge, which makes no sense, but I was trying to give you a gravitational analogy. And you've heard me talk about little q as little tiny satellite charge, which again makes no sense, but oh, and I've said that electric field is very, very similar to gravitational field. So what the heck is voltage? Well, we said this. Voltage, which is also potential, is how much energy per charge. That's kind of, if I want to go gravity-ish, to gravity potential, which would be potential energy per mass. And if you're close to the Earth, potential energy is mgh. Mass is m. What would happen to the m's? If you want a gravitational analogy to voltage, voltage is sort of like gravity times the height. In fact, I ignore G. Voltage, I treat voltage as height, Josh. If you ask me what does volts mean, it's similar mathematically to how high we've lifted an object. A higher voltage will do more damage when it hits the ground. In fact, in the next unit, when we look at circuits, we're going to treat it exactly like height. A 6-volt battery is like a chairlift on a ski hill that's twice as high as a 3-volt battery. And so if you're on a 3-volt battery, you can't get to the top of the mountain compared to a 6-volt battery. That's not a perfect analogy because, Zach, I'm really ignoring that little G in front of the H. Because we're just changing, whatever. So I think of voltage sort of, kinda, a little bit like height. Then, for what it's worth, if you want to, you can think of a parallel plate as a steadily sloping mountain and a point charge as a curvy mountain. It's taking it a bit far. What's your homework? Number 1. Number 2. Number 3. Mac, what does number 4 want me to find? Where? Between plates? You know what? I can't use... Don't write this down. Because they didn't give me 2 charges. Wait a minute. I could use this. If they gave me 1 charge, and if I could figure out the electric field that it's in, and I think I figured out the electric field from number 3. So use that for number 4. Nate, what's number 5 want me to find? Work? Work. You know what? Work is going to be change in potential plus change in although you know what, I don't think they're mentioning any change in kinetic. I'm not going to use the one that Mickey asked me where I have to go K Q1 Q2 over R final minus K Q1. I think I can just use or because the force is constant, you could also go where the force is QE. It'll work. So a little nicer. Grayson, what's number 6 want me to find? Electric field. Between plates or from a round circular charge? Well, it says from an what? Electron. You know what? That's a round circular charge. Use the electric field equation with an R for radius for round circular charge. Don't use voltage over distance. It's not going to work. Okay. 7 is kind of whatever. 8 is whatever. 9 is I'm just going to assign right now 1 through 6 and the take-home quiz.